In this video, we will do more examples on continuous random variables. Let's suppose that the density function of a random variable is defined in this way. F of x equal to c times x when x is between 0 and 2 and is 0 otherwise. In this case, the graph of that function is before 0 is 0. From 0 to 2 is a line with the slope c, and after 2 is just 0. This is the density function, and we want to compute the value for c. What is c? And also let's compute the probability that x is bigger or equal than 1. Then since this is a density function, we want the integral from negative infinity to infinity of f of x dx, which is just the probability that x is any number. We want this to be equal to 1. But this integral, when we split this integral into 3 pieces, negative infinity to 0 of f of x dx plus the integral from 0 to 2 of f of x dx plus the integral from 2 to infinity of f of x dx, then by definition the function before 0 is 0, then this is equal to 0. Also after 2 this is equal to 0, and here the function is given by c times x, and then just do dx, and this is just c over 2 x squared from 0 to 2, and this is 2 squared is 4. This is equal to 4 over 2c, and we want this to be 1, and that means that c must be equal to 1/2. And essentially this requirement that the integral from negative infinity to infinity of the density function to be 1, it means that the area under the graph must be 1. And here, since c is equal to 1/2, this is the graph of the function f of x equal 1/2 of x. That means that this point here is the point 2, 1, and this is a triangle, base 2, height 1, then this has area 1 as expected. To compute this probability, the probability that x is bigger or equal than 1, this is just the integral from 1 to infinity of f of x dx, and this is just the integral from 1. When we split this, it's going to be the integral from 1 to 2 of 1/2 of x dx plus the integral from 2 to infinity, and the function f of x after 2 is 0, and then this is just the integral of 1/2 of x, which is 1/4 of x squared between 1 and 2, and this is just 2 squared is 4 divided by 4 is 1 minus 1/4, and then this probability is 3/4. What is c? c is 1/2. What is this probability? This probability is 3/4. The interpretation for this probability is the area under the graph from 1 to infinity. Then this area here and this area here, there is no area here, but the area under the graph, this is 3/4. Since we have this example already, let's compute the expected value, and let's compute the variance and the standard deviation. This is our density function. Then the expected value is just the integral from negative infinity to infinity of x times f of x dx, and we end up with the integral from 0 to 2 of 1/2 x times x, 1/2 x squared dx, and this is 1/6 x cubed of from 0 to 2, and when I evaluate at 2, I get 2 squared is 4/3 minus 0. Then the expected value is 4/3. To compute the variance of x, we need to compute the integral from negative infinity to infinity. Let me remind you that this 4/3 is the expected value, which is denoted by mu. To compute the variance, we do the integral from negative infinity to infinity of x minus mu squared f of x dx, and this is doing the same argument. We just get the integral from 0 to 2 of x minus 4/3 squared times 1/2 of x dx. This is the integral from 0 to 2, and here we have 1/2 of x times x squared minus 8/3 of x plus 69 times dx. And this is the integral from 0 to 2. Here we have 1/2 x cubed minus 4/3 x squared plus 8/9 x dx, and this is x to the 4 over 8 minus 4/9 x cubed plus 4/9 x squared from 0 to 2, and then this is 16/8, which is just 2 minus 2 to the 3 is 8. 8 times 2 is 32/9 plus 2 squared is 4 plus 16/9 minus 0, and this is 2 minus 16/9, and this is just 2 over 9. Then the variance is 2 over 9, and the standard deviation is the square root of 2 over 9. A function that is going to be important is the cumulative distribution. Let me define that. Cumulative distribution. And in general, if we have a density function, the cumulative distribution is defined as the probability that x is smaller or equal than a. This is just f of a. And then, by definition, is the integral from negative infinity to a of f of x dx. This is the definition of the cumulative distribution for a random variable that is defined with a density function. Then if this is a density function, this is the cumulative distribution. In this particular case, we have that f of a is 0 if a is smaller or equal than 0, and when a is bigger than 0, then this integral, when a is bigger than 0, then the probability that x is smaller or equal than a is just the integral from negative infinity to a of f of x dx. But since a is bigger than 0, let's divide this into two cases. If a is bigger than 0 but smaller than 2, then this is just the integral from 0 to a of f of x dx, and this is just the integral from 0 to a of 1/2 of x dx, which is 1/4 of x squared between 0 and a, and this is just a squared over 4 minus 0, which is a squared over 4. Then when a is between 0 and 2, the function is a squared over 4. And when a is bigger than 2, then this integral, the probability of x smaller or equal than a, is just the integral from 0 to 2 of f of x dx, and we already checked that this is 1. Then the cumulative distribution is 1 if a is bigger than 2. Then we have the cumulative distribution. By the fundamental theorem of calculus, we know that the derivative of the cumulative distribution is just the density function evaluated at a. We can check that here. The derivative, if we have f of a equal to a squared over 4, then the derivative of a is just 1/2 of a, which is just f of a. Something that is going to be useful later on, since the cumulative distribution is an antiderivative of the density function, then anytime we want to compute the probability that x is between, let's see, some values, let's see, c and d, then this is just the integral from c to d of f of x dx, and this is going to be f of d minus f of c. This is going to be an important property. Essentially, the cumulative distribution is an antiderivative, then it allows us to compute the integral that we need to do when we want to compute the probability that the random variable is between two values. This is again the fundamental theorem of calculus. Let's do another example. Let's suppose that the amount of time in hours that a computer functions without breaking down is given by the random variable with a density function f of x equal a number c e to the negative x over 150 if x is bigger or equal than 0 and is 0 otherwise. Then the question is, what is the probability that the computer will last more than 100 hours? And what is the probability that the computer will stay without breaking down between 50 and 150? Okay, let's do these two problems. First of all, we need to find C. Remember that since this is a density function, we want the integral from negative infinity to infinity of f of x dx. We want this to be 1. Let me remind you that when you do the antiderivative of e to the x dx, this antiderivative is e to the x, and if you do the antiderivative of e to the 2x dx, then you have to do a substitution. You do u equal to 2x, then dx is just 1/2 of the u, or we say the u is 2 times dx. That means that the x is 1/2 of the u, and we end up that this is just 1/2 of e to the 2x. In general, the antiderivative of e to the kx is just 1 over k e to the x. We will be using this antiderivative. Then when we try to compute this integral, because of this splitting of the density function, this is just the integral from 0 to infinity of c times e to the negative x over 150 times dx. Right? But this integral is just negative 150 e to the negative x over 150 evaluated from 0 to infinity. Notice that you can check that if you do the derivative of this, there is a negative that comes down because of the inner derivative and a quotient of 150 that cancels with this 150. When we compute the antiderivative at infinity, we are computing a limit, the limit when x goes to infinity, but since there is a negative here and e to the very large negative number is very close to 0, you can try in your calculator like e to the negative 100 or e to the negative 1000 is a very, very small number. Then this limit is just evaluated at infinity, it is 0, and when you evaluate at 0, you get negative 150. That means that, sorry, I forgot the c. This is negative c times this, and here we have negative 150c, and then this is positive 150c, and we want this to be equal to 1. That means that our c must be 1 over 150. Then this c here is 1 over 150. Now that we have the density function, we can compute these two probabilities. First, the probability that x is bigger than 100 is the integral from 100 to infinity of 1 over 150 e to the negative x over 150 dx. And this antiderivative is just negative e to the negative x over 150 evaluated from 100 to infinity. Same argument as the one that I did here. When you evaluate at infinity, that limit gives us 0, and when you evaluate at 100, this negative and negative becomes a positive, will be plus e to the negative 100 over 150, and this number is equal to 1 over e to the 2/3, which is 0.5134 approximately. To compute the probability, let me write this down. This is approximately equal to 0.5134. And to compute the probability that the computer will break down between 50 hours and 150 hours, then we just do the integral from 50 into 150, and the only thing that changes here is that we have a 50 and a 150, and then the answer is going to be negative e to the negative 150 over 150 plus e to the negative 50 over 150, and this is negative e to the negative 1 plus e to the negative 1/3, which is approximately equal to 0.3487. Then this probability here is approximately equal to 0.3487. Just as an example, let's compute the cumulative distribution for this density function. Notice that the graph of this function is like this. Is before 0 is 0, and after at 0 is equal to 1 over 150, and then after that is just an exponential decay. The cumulative distribution by definition is the probability that x is smaller or equal than a. This is f of a, and then we get that this, if a is smaller than 0, then we're integrating the 0 function and then we get 0. But if a is bigger than 0, then this becomes just the integral from negative infinity to a of f of x dx. But because of the definition of the density function, before 0 is 0 and after 0 is equal to that, then this splits into the integral from 0 to a of 1 over 150 e to the negative x over 150 times dx. And this is just negative e to the negative x over 150 from 0 to a, and when you evaluate at a, you get negative e to the negative a over 150, and when you evaluate at 0, you get minus negative 1, which is plus 1. Then this function is just 1 minus e to the negative a over 150, and the graph of this function, the graph of the cumulative function, would be something like this. When a is 0, this is 0, and when a is very, very big, it goes asymptotically to 1, right? This is 1, and this is like an exponential function going down. Then the graph would be like this, and then after this is 0. We can check that the derivative of this function is just this function, and again I want to emphasize that for that reason we have that the integral from c to d of f of x dx, which is just the probability that the random variable is between c and d, is just the cumulative function evaluated at d minus the cumulative function evaluated at c. Let's do one last example. Okay, this problem says that the lifetime in hours of a certain kind of radio tube is given by this random variable. And actually here we need to write a c, and then the question is find a c and find the probability that the radio tube will last less than 200 hours. Let's see how to find C. In this case, the graph of this function, notice that the splitting happens at 100 and the density function is 0 before 100, and it is of this form, is of the form C over x squared. That means that this graph goes like this. We want this area under the graph to be equal to 1. Let's compute this integral. The integral from negative infinity to infinity of the density function, because of this splitting, is just the integral from 100 to infinity of C over x squared is the same as C x to the negative 2 dx, and this is the antiderivative of C x to the negative 2 is negative C x to the negative 1 between 100 and infinity, and this is negative C over 1 negative C over x between 100 and infinity. And when I evaluate at infinity, I'm taking the limit when x goes to infinity, but that limit is 0, and then it will be 0 minus, and when I evaluate at 100, is negative C over 100. That means that this integral is C over 100, and since we want this to be equal to 1, therefore C must be 100. And this must be 100. Now, this probability is just the integral from negative infinity to 200 of the density function f of x dx. But by the way this function is defined, the integral up to 100 is 0, and then this will be just the integral from 100 to 200 of 100 over x squared dx. And this is equal to negative 100 over x between 100 and 200, and this is negative 100 over 200 minus negative 100 over 100, and this is just 1 minus 1/2, which is 1/2. Then this probability is 0.5.